Hello, it is great to see you again. Our solar system is a truly wondrous place, with countless celestial bodies scattered across billions of kilometers of space, all being pulled around the galaxy by the sun like a sophisticated, synchronized machine. The small planets located near the center are made of rock, and at least one of them harbors life. The giant planets further out are instead enveloped by gas and ice. They themselves are like miniature solar systems with rings and their own complex satellite systems. Scattered throughout the solar system are also smaller celestial bodies, such as rugged asteroids, comets, and complex dwarf planets like Pluto and Ceres. So, exactly how did the solar system form? How did they evolve? Why are these celestial bodies in their current positions? Here is the sequence of events that created and shaped our solar system, based on the best current understanding synthesized from space missions, observations from Earth, and complex simulations performed by scientists. Welcome to the history of the solar system. 13.8 billion years ago, the Big Bang created the universe. 4.6 billion years ago, a group of protostars formed from the collapse of fragments inside a giant molecular cloud. The specific fragment that formed the solar system, known as the Solar Nebula, was approximately 3.26 light-years wide. The massive parent cloud, about 65 light-years wide, orbited the center of the Milky Way and contained 99% gas, primarily hydrogen with some helium, and 1% dust. Dust within the molecular cloud consists of microscopic particles containing heavy elements like carbon, silicon, oxygen, and iron, formed from previous stellar explosions in the Milky Way. In other words, the death of other stars contributed to the creation of our own star. Shockwaves from one or more supernovae exploding near the solar nebula may have triggered widespread disturbances, initiating the process of gravitational collapse. Over the next 100,000 years, this cloud collapsed into several hot and dense objects called protostars, including our Sun. During that process, the conservation of angular momentum caused the solar nebula to begin spinning. Over time, the solar nebula spun faster and faster, flattening into a protoplanetary disk roughly 200 astronomical U in diameter, with a newborn star at its center, an unweaned version of our Sun. While the infant Sun was actively accumulating material, small dust grains in the surrounding disk randomly collided and stuck together, developing within just a few years into bodies hundreds of meters in diameter. This eventually led to more collisions and further accretion of matter, forming moon-sized protoplanets in less than 1 million years. 4.59 billion years ago, the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed around the proto-Sun. In the cooler outer regions of the disk, gas and water ice were the primary components. Here, the Sun's weaker gravity combined with an abundance of material helped protoplanets grow rapidly until they were large enough to attract light elements like hydrogen and helium. The result is that Jupiter formed less than 3 million years ago, after the solar system was born, making it the oldest planet. Saturn appeared shortly after, slightly smaller because Jupiter had already vacuumed up most of the outer disk. As the saying goes, whatever is in this house belongs to me. I am the boss. By the time Uranus and Neptune got their birth certificates, very little hydrogen and helium remained. So these two had to accumulate more icy materials, such as water and ammonia. For this reason, we call them the ice giants, while the two big boys, Jupiter and Saturn, are called the gas giants. Some simulations suggest that additional ice planets may have formed, but were eventually ejected from the solar system. We will discuss this further in a later part. Scientists believe the giant planets formed closer to the Sun than their current positions, at least for Uranus and Neptune, as there wouldn't have been enough matter to form these two giants at their current locations, which are 19 and 30 times further from the Sun than Earth is. The Kuiper Belt may also have formed closer, extending into the current orbital ranges of Uranus and Neptune, and was once much more densely populated than it is today. 4.55 billion years ago, the baby sun began the process of nuclear fusion, converting hydrogen into helium. The first solar rays appeared. Our infant sun continuously accumulated matter over the next 50 million years. Gravitational pressure caused the temperature and pressure to become so intense that hydrogen in the core began to fuse into helium, and then light was born. The energy released from the nuclear fusion in the sun's core countered the inward pull of gravity, preventing the young star from collapsing and stopping it from accumulating more matter from the surrounding protoplanetary disk. At this point, the sun reached hydrostatic equilibrium and entered the main sequence phase, the longest and most stable period of its life. Kainan, after 4.5 billion years, the sun is still in this phase and will remain so for about another 5 billion years. 4.5 billion years ago, Mercury, Venus, Earth, and Mars formed. A Mars-sized planet collided with Earth, and the resulting debris formed the Moon. In the inner part of the solar protoplanetary disk, where temperatures were higher, planets formed primarily from rock and metal because it was too hot for water and other volatiles to condense. Hundreds of such bodies collided and merged over about 100 million years in the inner solar system, until only 4 large bodies remained: Mercury, Venus, Earth, and Mars. The inner planets are not as large as the outer planets because, as mentioned before, the proportion of dust, rock, and metal accounted for only 1% of the original molecular cloud. Somewhere around this time, a Mars-sized planet collided with Earth. The debris from this collision merged to form the Moon. This is known as the giant impact hypothesis. Mercury may have also experienced a high-speed collision with another planet, stripping away its outer crust. This explains why this planet's core occupies such a large portion of its volume, at least when compared to Earth. Debris from that collision likely scattered into space rather than forming a moon. Jupiter prevented large celestial bodies from forming within the asteroid belt, because its massive gravity tugged on early planets similar in size to the Moon or Mars, causing them to collide and shatter, or migrate out of the region. This process lasted tens of millions of years after Jupiter's formation, leaving behind an asteroid belt with only small bodies made of rock, ice, and metal, totaling less than 1% of Earth's mass. Ceres, the largest body in the belt, is considered an exception because it contains many organic compounds and water ice, suggesting this dwarf planet might be an immigrant, meaning it formed further away before moving into the belt. As the inner rocky planets were forming, early planets, located beyond Neptune, also collided and stuck together, creating dwarf planets like Pluto and odd-shaped icy objects like Arakoth. These bodies make up what we now call the Kuiper Belt. Collisions within this icy belt likely created Pluto's moon, Charon, similar to how our moon appeared. A large object in the Kuiper Belt may have struck Pluto at very high speed, causing massive destruction and blowing away much of the dwarf planet's outer shell, with Charon reforming from the debris. Further in, Jupiter's massive bulk attracted a dense disk of material which eventually merged into 4 giant moons: Io, Europa, Ganymede, and Callisto. Saturn's moon, Titan, likely formed in a similar way. Elsewhere, some moons of the outermost planets, such as Neptune's Triton, may have once been free-floating planets, kidnapped by the ice giants. And that, from what we know, is the end of the beginning. After about 100 million years, the accretion process for planets and small bodies ceased, as powerful solar winds from the young and vigorous sun blew away most of the remaining dust and gas into interstellar space. So how will the solar system continue to evolve? When did the Sun begin to separate from its protostar siblings? Who pushed Uranus and Neptune further away from the Sun? What triggered volcanism on the rocky planets? Or at what point did life emerge? The answers will be in part 2 of this video. We invite you to watch it tomorrow. Remember to do the 3.5-step process. Like, share, subscribe, and ring the bell so we stay motivated. For now, goodbye, and see you again.